In this tutorial, I'm going to talk to you about how to set up an input file for an assimilation and fractional crystallization, or AFC run. So to get to those input files, remember, navigate to your Finder, then Documents, and into the MCS folder structure. Input files, as a reminder, are located in the Input and Output folder. Now we're going to use this file called MES_AFC. This is actually a pre-populated input file that you should have received with your MCS folder structure. So I'm going to make it just a smidge bigger so everybody can see it. And the first thing you'll notice, again, are your global system parameters. In the past, in previous tutorials where we have not done assimilation, we've set our FM0 at 1. Because we do want to assimilate here, we're going to set this value to somewhere between 0 and 1. So FM0, as a reminder, is the minimum mass fraction of liquid that must accumulate in the wall rock before assimilation is triggered. To be more specific about it, let's say I want to make any amount of liquid over 5% transfer from the wall rock to the magma. So if I set my FM0 at 0.05, as heat is transferred from the magma subsystem to the wall rock subsystem, the wall rock will start to melt. Once 5% of the wall rock is liquid, then assimilation is triggered. Now that 5% doesn't get transferred. Anything above 5% gets transferred. So say we get to a point where 6.42% of the wall rock is liquid. If we've set our FM0 at 0.05, anything above 5% liquid gets transferred from the wall rock to the magma. So we would be assimilating 1.42% of the wall rock. Next is excluded phases. For this simulation, I'm not going to exclude anything, but if you'd like to, again, I suggest using the Exclude Phases button on the interface for the magma chamber simulator. For the next parameter, system pressure, we're going to be running this at 2 kilobars. As a reminder, these system variables do get globally applied to the magma, wall rock, and recharge subsystems. So all of our subsystems are going to be run at 2 kilobars. For enthalpy convergence steps, because we are dealing with some isenthalpic calculations here, should probably stay at 30. That's our sweet spot. But if you'd like to play around with it a bit, values can range anywhere from 10 to 100, and, enjoy. For oxygen fugacity for this run, we're going to be running at FO2 is absent, so we're not going to have any FO2 buffer that we're going to be restricted to. If you would like to change that, input values are given in column F. So here we can do none, FMQ, COH, NNO, IW, or HM. Those are your standard oxygen fugacity buffers, coarse phthalate, magnetite, iron woostite, so on and so forth. Just make sure that when you put them in, you put them in as is. So if you're used to running along the QFM buffer, again, notice that QFM is not QFM here. QFM is FMQ, and it is in lowercase. So make sure you put things in exactly as they are. Switch that back. Now for our magma composition. So here we have basalt. I've already normalized this to 100. Again, all of your compositions do need to be normalized to 100. So if you're adding some water, taking something out, make sure you've renormalized your composition before putting it into column B. Our starting temperature for this magma is going to be at 1300 degrees. Now again, we're not necessarily starting at 1300 degrees. The magma subsystem goes automatically to the liquidus and then crystallizes and cools from there. The temperature decrement for cooling of the magma subsystem is set at 5 degrees. In prior tutorials, we've set the next parameter, the hard stop temperature, at some temperature, some number, 800, 850, because we weren't really interested in what was happening at lower temperatures than that. With assimilation, though, we might want to see what happens at lower temperatures as you start to assimilate more and more and more and more wall rock. So if we don't want to set a hard stop temperature, go ahead and put 0 in here. The MCS run will finish when the wall rock subsystem and the magma subsystem are thermally equilibrated. Now this can take a while, but if that's what if you're interested in stuff that's happening at lower temperatures, I would definitely advise leaving this at 0, and then the MCS will go ahead and ignore it, and then stop the run when magma and wall rock have equilibrated. For the wall rock composition here, we have a really nice Sierra Nevada granitoid. Again, it's been normalized. And notice that I have CO2 in this composition. This is just an aside. If you're not familiar with the different versions of Rhyolite-MELTS, please go to the OFM Research website and take a look at what the different versions should be used for. Because we have CO2, I'm definitely going to be running this using version 1.2.0. The next parameter for wall rock is our wall rock find Solidus temperature. So this, you want to put some temperature that's below the solidus of the wall rock. To find that out, if you're not sure, I definitely recommend running this composition through standalone melts at the pressure and oxygen fugacity that you're going to do your MCS run at, so you know exactly where the solidus and liquidus temperatures are for your wall rock. Really, I advise doing this for every single composition that you plan to use, because that way, you don't run into error messages as often. You already know where the liquidus and solidus are for each composition, and you don't mess up as often. The next parameter is our temperature decrement for the wall rock prime. So during the initial wall rock prime, when the MCS is trying to figure out what the parameters of the wall rock are, where's its solidus, where is its liquidus, and so on and so forth, this is the temperature at which the wall rock will cool by. I actually like it a little bit bigger than this. I like to set mine at 25, and that makes the process go a little bit faster. Third parameter for wall rock is your start temperature. So you don't necessarily have to go above the liquidus, but as a general rule, I like to, especially if you're going to set your temperature decrement high, then it still doesn't take as much time. If you set your temperature decrement low, you can kind of balance out the time issue by setting this value to a temperature just above what is required to melt the wall rock for whatever your FM0 is set at. So if my FM0 is set at 0.1, that means that 10% of the wall rock needs to melt. So I could set my find solidus start temperature to some temperature just above whatever temperature is required for 10% of the wall rock to be liquid, and this would work just fine. The next parameter is the initial wall rock solid mass. In prior tutorials where we've tried to turn off assimilation, I've had this value very large, 10,000 grams, 1,000 grams. But here where we're trying to assimilate, we want this value to be reasonable or small. Here we have a 1-to-1 ratio. So the magma is initially 100 grams. Our wall rock will be initially 100 grams. And this facilitates assimilation just a little bit easier. The final wall rock parameter is the initial temperature of your wall rock. So in prior tutorials, I've had this low. I've had it at 400 degrees. But the higher the initial temperature of the wall rock when your simulation starts, you don't need as much heat to be transferred from the magma subsystem to the wall rock subsystem before the wall rock starts to melt. So if I set this, say, at 600 as opposed to 400, I'll start assimilating sooner. If I set this even higher, if I have my initial wall rock temperature at 750, which is not realistic, but, if you're working with crystalline mushes, hey, you never know, then it would take even less heat to be transferred from the magma to the wall rock subsystem before assimilation is triggered. The final thing we need to look at is our recharge. Again, we're not doing recharge in this tutorial or in this simulation, so we can go ahead and turn it off. To do so, I just clear contents for these bottom two cells, and I scroll on through and just make sure that all of my recharge events are turned completely off. So that concludes this tutorial on how to prepare an input file for an assimilation and fractional crystallization run. In another tutorial, we'll learn how to do this for a recharge and fractional crystallization run, and then we're going to learn how to actually use the magma chamber simulator.